Hello everyone, I'm Ron from the Center for Turbulence Research at Stanford University, and today I'd like to share my work on the subgrid-scale modeling of bubble breakup in large eddy simulations of breaking waves. So I've been supported by the Agency for Science, Technology and Research in Singapore, and some of the computational work was also supported by the Department of Energy. Bubbles are formed in abundance in these breaking waves in the ocean, and their sizes range from micrometers to millimeters, and they have a significant influence on acoustics, light scattering, and carbon capture. And today I'll just highlight two key examples of the influence of these bubbles. So firstly, ship wakes. When fast-moving ships move quickly through the ocean, they generate bow and stern waves, which break to form bubbles of various sizes. And because the smallest bubbles in these wakes take a very long time to rise to the surface, these ship wakes may persist for as long as kilometers, and they are detectable by sonar as well as satellite imaging. Another example is the marine carbon cycle. So here I'm showing a schematic depicting the exchange of carbon dioxide between the atmosphere and the ocean. So you can see from the schematic that one primary mechanism for the entry of carbon dioxide into the ocean is dissolution, and breaking wave enhances this dissolution by generating bubbles. So quantifying the contribution of breaking waves to this dissolution of carbon dioxide would enhance our understanding of the marine carbon cycle, with numerous implications, such as a better understanding of the generation of hurricanes, as well as a climate emergency. Now, the sizes of these bubbles have been measured in various experiments, including this one by Dean and Stokes. As you can see from this size distribution and plotting, the smallest bubbles that they measured had the size of approximately 100 microns, which is at least 4 orders of magnitude smaller than a wavelength. So this means that bubbles in these breaking waves span a wide range of sizes and are extremely costly to directly simulate, necessitating subgrid scale models to bring down their cost. So in our previous work, we showed using theory and simulations that turbulence breaks the large bubbles in a system, carrying gaseous mass from a large bubble size to a slightly smaller size to a slightly smaller size, and so on and so forth, all the way to the Hinze scale. Now this means that the bubble mass transfer that takes place is size local, justifying the presence of a breakup cascade. Now in this cascade, there is a separation of scales. So the large scales are influenced by the flow geometry, but the small scales, the Hinze scale, they have universal behavior. And what I mean by this is that small bubbles break up independently of the details of the large scale dynamics. So what does this scale separation mean for us? This means that we can implement a cascade-based subgrid scale model to model these small scales. So these subgrid scale models can be applicable to various turbulent bubbly flows, because remember, this breakup doesn't depend on the large scales. And because of that, these models can enable cost-effective full-scale simulations. Now, I just wanted to highlight that while this transfer of bubble mass is strongly local, it turns out that it is also slightly leaky. There is indeed some non-local transfer. And it turns out that we can model this directly with the direct generation of microbubbles. So carrying air mass from the large scales directly to the very small sub-Hinze scales. So the inset over here on the bottom left corner shows sort of a schematic depicting how we might implement such a model. And we have addressed this in our previous work, and I've shared some of these references in bold below. However, this is more or less a secondary mechanism for the generation of bubbles. Today, we want to focus on the cascade-based subgrid scale model, which is a primary mechanism for the generation of these small bubbles. So we'd like to propose this subgrid scale modeling paradigm in direct analogy to the simulation of single-phase turbulence. So in other words, large eddy simulations, or LES. So what is done in LES, so if you treat this instead as an energy spectrum, is that the large scales are resolved, the small scales are modeled, And the small scale dissipation rate has to match the large scale production rate. So we want to carry this analogy directly to bubble breakup. So let me walk you through what we have in mind. So we intend to resolve large bubbles and the wave surface by an Eulerian interface resolving method, such as a volume of fluid scheme. So in the inset, I have an example of one of these simulations, so a large-scale simulation. So in this case, all the bubbles are larger than the grid size, they're resolved, and they are captured in an Eulerian fashion. And this, of course, this solver resolves large bubble breakup into bubbles of various sizes. Now, small bubbles are also generated in this process, and some of them turn out to be under-resolved. So step one of our model will be to transfer these under-resolved Eulerian bubbles to become Lagrangian point particles. Once these bubbles are generated, they are then advected by the flow solver in tandem with the Eulerian phases, the liquid and gas phases described by the Eulerian solver. However, we further break these Lagrangian bubbles down into smaller and smaller bubbles successively all the way to the Hinze scale, where the breakup cascade is then terminated. So this generates another size distribution of bubbles at these modeled scales. Now, just like in single-phase LES, we sort of need to match the Eulerian and the Lagrangian behavior. So we can do this by matching the breakup flux of the Lagrangian particles to the breakup flux of the larger resolved bubbles. So we know from theory, simulations, experiments that the large bubbles follow a d to the negative tenth sort of quasi-equilibrium power law distribution. This turns out to be consistent with a constant bubble mass flux and a breakup frequency that scales as the size of the bubble to the power of negative 2/3. And in order for the small scale flux to match the large scale flux, the small scale flux also has to follow this breakup frequency. And this is the constraint that we implement in our model. So at this point, let's ask a question. So what happens when we have a large bubble population for initial d to the negative 10/3 power law distribution, like in a breaking wave? What will happen when we start to break these bubbles up? It turns out that the small bubble population is initially not negative 10/3, as you can see from this sort of olive colored line at the top. But as time progresses towards this dark blue line, eventually, after one integral time, the small bubble population also approaches the quasi-equilibrium d to the negative 10/3 power law distribution. And we were able to verify this a priori by performing stochastic breakup of a population of artificial bubbles. Now, before I move on, I just wanted to point your attention to this peak at the Hinze scale. So this peak occurs because we didn't want to make any ad hoc assumptions at the Hinze scale for now. So what we did was the following. We allowed breakup to happen above a prescribed Hinze scale, but not below the prescribed Hinze scale. This means that bubbles, they break, and then they are not allowed to break. So this causes a small power of bubbles at the Hinze scale, which we will revisit later in this presentation. Now, because we saw this quasi-equilibrium behavior after an integral time, this motivates us to test a posteriori a quasi-equilibrium subgrid-scale model in our flow solver. What do I mean by this? Remember I said that these Lagrangian bubbles successively break into smaller bubbles through individual events. So what we prescribe here is that in each Lagrangian breakup event, the generated children bubbles are sampled from a d to the negative 10/3 size distribution. So not the entire Lagrangian population, but each event and its children bubbles. So we implemented this subgrid-scale model in an unstructured geometric volume of fluid solver. So I have a screenshot here of the initial conditions of such a wave. So this solver is documented in these references here. So the grid size of this simulation is such that this is approximately a 216 cube. simulation. And the Eulerian to Lagrangian transfer occurs approximately 2 to 4 times larger than the grid size. And just wanted to state here that the wavelength we're simulating is a 27 centimeter deep water wave. So slightly smaller than the experimental waves I was talking about earlier. Now I just want to walk you through what we expect to see in our results, because the distribution can be a bit confusing. So let me walk you through step by step, sort of the pieces and the characteristic scales in this problem. So with no subgrid scale model, only bubbles larger than the grid scale are resolved. So you see here d to the negative 10 distribution above the grid scale. So this is what we expect when there is no subgrid scale model and all the bubbles are Eulerian. Now let's look at what happens when we have an ideal subgrid scale model. So remember, the subgrid scale model has 2 steps: transfer from Eulerian bubbles to Lagrangian bubbles, and then the subsequent breakup, successive breakup of Lagrangian bubbles to smaller and smaller sizes all the way to the Hinze scale. So now you see that the bubbles between the grid scale and the transfer scale are now Lagrangian, because transfer occurs near the transfer scale. In addition, bubbles are also generated below the Hinze scale. So between the Hinze scale and the grid scale, we also expect a d to the negative 10 distribution. Below the Hinze scale, there has not been a mechanistic explanation for the generation of these bubbles, but some studies, experimental and numerical, have seen this d to the negative 3/2 distribution. So you might expect to see this as well in an ideal subgrid scale model. And of course, eventually bubbles dissolve and the size distribution should drop off towards the left. Now, what happens when we don't have an ideal subgrid scale model? So one possibility is that what I mentioned earlier, if we set the bubbles to abruptly stop breaking at the Hinze scale, which prevents us from making ad hoc assumptions, but it's also not entirely realistic, then bubbles start to pile up below the Hinze scale. And you will see a peak that occurs to the left of the Hinze scale. I just wanted to point out that with some phenomenological assumptions, such as a PDF for the Hinze scale, we can mitigate this kink over here, as mentioned, as discussed in this reference below. So we're not too worried about this. What is more important probably here is that if the breakup flux, as I mentioned, it is crucial that the small scale flux matches the large scale flux. So what happens if this flux is mismatched? Now the small scale flux is too large compared to the large scales, then the small bubbles start to break, or to break too quickly. This means that the number of small bubbles will decrease and this curve will shift downwards. And because they break more quickly, the pile up below the Hinze scale also happens more quickly. So expect this kink to be magnified as well. And one thing I want to point out here is that the bubble size distribution I'm describing here actually is normalized such that, roughly speaking, the area under the curve should sum up to the number of bubbles and not 1 as you would expect in a normal PDF. So this is why when there are fewer bubbles, the curve should shift downwards, and if there are more bubbles, the curve will shift upwards. So this is sort of how we chose to normalize the size distribution. So if the breakup flux is not matched, we will expect to see several kinks as I have described in this schematic. So with this information in hand, let's look at what distribution we observed in our simulations. And before that, sorry, let me mention too, that we also verified this behavior through a priori analysis. So again, we did stochastic breakup of an artificial population, made the small bubble flux larger than it should be, and we also observe this behavior I'm showing here with the purple arrows. So with this in mind, let's now look at the a posteriori distribution. So I'm plotting here a time average distribution, average over the second integral time after the breaking occurs. We will have to refer to our previous work, but we showed in our previous work that within this time interval, we expect that the large bubbles, intermediate size and large bubbles, obey a negative 10 power law of scaling. So here I'm plotting a negative 10 power law scaling at large sizes, negative 3/2 power law scaling at small sizes. So these are the two dashed and dash dotted reference lines. The green dots represent the distribution obtained without a model, so just Eulerian bubbles. And the dark blue points represent the distribution with a model, so Eulerian to Lagrangian transfer and then Lagrangian breakup. So you see that above the grid resolution, the two distributions are coincident, which we shouldn't take for granted, because if we don't do this matching of, well, if we don't do this transfer and breakup properly, it turns out that these two distributions might not match. So that is one of the first observations, that these blue and green distributions do match. And everything you see to the blue left of the blue dotted line, these are all subgrid bubbles. And the black line is where we prescribe our Hinze scale to be for this system. So we have 4 key observations in this distribution. So let's begin in the bottom right corner. For this super grid scale bubbles, we expect a negative 10 power law scaling, and we do indeed see this, both with and without the model. So without the model tells us that gives us confidence in this distribution above the grid scale, and the agreement between the two tells us that the model is not sort of distorting the super grid distribution. Now let's go to the bottom left corner text box. So the negative 3/2 scaling, as I mentioned, was observed by several experiments and simulations. And we do observe this scaling at small scales. So this tells us that, well, we do manage to recover this scaling. Let's move on to the top left text box. As I mentioned earlier, we expect the king near the Hinze scale. And we do in fact observe this because we did not have any special treatment of the bubbles near the Hinze scale thus far. So right now we have no ad hoc assumptions. So this means that we expect accumulation below the Hinze scale. The final observation is at the top right corner. So the text box at the top right corner. Well, we see some kings near this grid resolution, and this tells us that the Eulerian to Lagrangian transition, so the matching of fluxes I was discussing earlier, needs to be improved. And it is sort of something we're working on right now. So just to conclude, subgrid scale models are required for cost-effective simulation of turbulent breaking waves, especially the largest waves in the ocean, where the wavelength can stretch up to tens or hundreds of meters even. And to simulate these waves requires subgrid scale models, and as I mentioned, turbulent bubbly flows in general, because since turbulent breakup occurs via a bubble mass cascade, we know that the breakup is size local and a small scale breakup is universal. This means that any subgrid scale model we develop has the potential, of course we need to confirm it, but it has the potential to be generalizable to various turbulent bubbly flows. So today I have described a cascade-based model that we have implemented in an actual flow solver with reference to some a priori testing, so that we know what's going on in the a posteriori implementation. And we use this flow solver coupled with a model to feasibly simulate a breaking wave. We saw that the supergrid distribution is still physical. The subgrid distribution requires some improvement, and more investigation is needed into appropriate treatment at the Hinze scale, as well as the correct determination of the breakup rate magnitude. But because we have an a priori sort of sandbox, a Monte Carlo sandbox, in the a posteriori implementation, we can now go back and forth the two to see what is going wrong with the a posteriori implementation, go back to the a priori testing to understand where sort of these discrepancies are coming from to iterate and improve this model. So with that, this is the end of my presentation. Thank you for watching this. So again, I want to thank the support from A-Star Singapore as well as the DOE. My contact information is on the bottom left corner. And here's a link to this gallery of fluid motion submission that we did 2 years ago. So if you scan this QR code, you'll be able to watch this video. Thank you for your attention, and I welcome any questions during the on-demand interactions. Thank you.